right, so today we're going to look at lesson 17.2, which is the fundamental theorem of algebra. You'll notice that a lot of what we're going to do with the first few examples looks like the extra credit assignment I had given you, which is why it had to be done before we did this lesson. So anyway, the fundamental theorem of algebra is a theorem that states that the polynomial p of x, so let p of x be a polynomial function of degree n, where n is greater than 0. Now, if the degree is 0, that would make it a constant. So all this is saying is that the polynomial is linear or higher degree than that. So if it's linear or more, the fundamental theorem of algebra says that the polynomial has at least one 0 in the complex number system. So meaning, if we include the imaginaries, that as long as its degree is 1 or more, that there has to be at least one 0 or at least one solution. So as a consequence of this theorem, this is what the theorem actually says. But what most people remember about the fundamental theorem of algebra is that whatever the degree is, as long as it's greater than or equal to 0, that means that that particular polynomial has exactly n linear factors, counting factors that are used more than once. So if it's used more than once, we count it more than once. Which as a result of that, that means that whatever the degree is, that's how many zeros there are if we count the repeated zeros more than once. So if we look at the example that they have here, we've got f of x, a polynomial. It's in standard form. It's degree 3. So the fundamental theorem of algebra would tell us that this has to have 3 zeros. So yesterday we reviewed how to find those zeros. Yesterday we reviewed how to factor the expressions, which helps us get the zeros. So to find the zeros, we set the function equal to 0, so that's step 1. Then we need to solve it. Well, we don't have any other way of solving polynomials with 4 terms, so we better hope that it's factorable here. So as we look at that, we are going to factor it by grouping. So x squared plus 2 times 3x plus 2 equals 0. And then, because it's now fully factored, we can use our zero product property, so set each factor equal to 0 and solve. So notice when we list the solutions that there are 3 of them: positive I radical 2, negative I radical 2, and negative 2/3. So 3 zeros, degree 3. That's what our fundamental theorem of algebra is going to help us with. So we're going to look at just a few of the try these here together, and then you'll have some to practice on your own. So the first one that I want to look at is letter C, this h of x here. So this problem I wanted to pick because it's similar to one that we looked at from your homework last night, where actually, we have kind of a linear factor as a variable. So if we think of this x minus 2 as if it were like a y, for instance, this is in the form y squared plus 4y plus 4. So if we think of it like that, then we can look at it to think about whether it factors or not. So I just need to know if there are factors that multiply to 4 and add to 4, which, yes, there are 2 and 2. So this actually, believe it or not, is a PST if we go through our factoring checklist, because the square root of the first term is x minus 2. The square root of the third term is 2. The sign in the middle is positive. And if I square this, I do get back this guy here because it'd be x minus 2 times x minus 2, which gives me this. Outsides and insides would both give me 2 times x minus 2. So since they both give me that, the total is 4. And then 2 times 2 is 4. So this is our factorization here. Now, obviously, once I have it factored, I can simplify that on the inside of the parentheses. So x minus 2 plus 2 is actually just x, so I've got x squared. So remember that when I'm solving, I'm setting it equal to 0. So I've got 0 is equal to x squared. So that's easy to solve. Take the square root, x equals plus or minus 0, which gives me 2 actual solutions. They just happen to be the same solution. So x equals 0 is the answer. That's our 0, but it's what we call a double root. The reason why we need to indicate that is because the directions here on Try These A tell you, and we'll look at them exactly. Sorry, accidentally minimized it. Find the zeros by factoring and using the zero product property. Show that the fundamental theorem of algebra is true by counting the number of complex zeros. So when I count them, remember that I count double roots however many times they appear. So this 0 appears twice. So that means that when I count it, I have one double 0. So one double root, which means it gets counted twice, so 2. If I were to multiply this all out, it would be quadratic. So degree is 2, number of roots is 2 because it's a double root. All right, let's look at another one. Going to look at f here, which is w of x equals x cubed plus 216. So when we look at this one, if I want to solve it by factoring, I need to put 0 in. So I've got 0 equals x cubed plus 216. If I follow my factoring order of operations, there is no GCF here. So after GCFs, I look for special products. And this one happens to be one of the special products that we just learned yesterday. This is a sum of cubes because my first term and my second term both have perfect cube roots. So when I look at this, I use my SOAP format for my signs. So I know it's going to be a binomial times a trinomial. I know first sign is going to be the same, so positive. Second sign is going to be opposite. Third sign is always going to be positive. So now I just need to fill it in. Binomial. Cube root of the first goes in the front. Cube root of the back goes in the back. And now remember, don't look back at the original to do the trinomial. Look at the binomial. So square the front to get the front. Middle multiply. And square the back to get the back. So remember also that I said yesterday that when you factor a sum or a difference of cubes, that the quadratic that is left is never going to factor further. So when I go to use my zero product property, I've got x plus 6 equals 0, which gives me x equals negative 6. But this guy is still quadratic, and I can't factor it further. So that means that I need to solve this via another algebraic method. So here it says math tips. The quadratic factor, it says to find the zeros of the quadratic factor. It says use the quadratic formula. Put next to this or complete the square, because sometimes completing the square is faster. And this is actually a case where completing the square is faster because a is 1 and b is even. So if I want to solve for x here, I am going to complete the square. If you prefer the quadratic formula, that's perfectly fine. You're allowed to do that. So I moved my constant over first. There is no a to factor out. If you prefer to write, a 1 in front just, to keep the completing the square steps the same for every problem, you can do that, but you don't have to. So then I add blanks. Then I need to do b divided by 2 squared. So b is -6. Divided by 2 is -3. -3 squared is 9. So my blank on the left side is 9. On the right side, it's also going to be 9 because 1 times 9 is 9. So then factor my left side. That's x minus 3 squared. Right side, I need to combine like terms, which gives me -27. And so now I can solve it. Square root on each side. That gives me x minus 3 equals plus or minus the square root of -27. So because it's negative, I know there's going to be an I. 27 breaks down. It's 9 times 3, which is 3 times 3 here. So 3 radical 3, and then I know there's an I. So plus or minus 3i radical 3. And then my last step to get x alone is to add the 3. So I end up with 3 plus or minus 3i radical 3. So this is a 0, -6 is, and then my additional zeros are down here. There's 2 of them. So we have 3 total zeros. Up here we wrote 1 double root to indicate degree 2, and I have 3 zeros, and my degree is 3. So it does match here. Okay, I'd like you guys to practice a couple of these on your own here. So if you turn the page to page 272, you should see a check your understanding box. And so the ones I want you to do in the CYU box are number 3 and number 4. So please pause the recording for a few minutes. I would say 5 minutes maybe. Shouldn't take more than 5 minutes to do that. To do the CYUs, and then when you unpause, you can check your answer. All right, so the first CYU that was here, when I go to solve this, and the directions are the same as the ones we just did, so we're going to factor it. When I go through my steps of factoring, step 1 needs to be hit here because there is a GCF of x squared. So when I take that out, I end up with x squared and x squared plus 25. So these are both quadratics. This quadratic does not factor any further because there's no such thing as a sum of squares. If this were a minus, that would be different. But this one does not factor any further, which means I need to go ahead and set each factor equal to 0 using my 0 product property. So I set each factor equal to 0. Here, I take the square root of both sides. X equals plus or minus 0. So that gives me x equals 0, but it's a double root. So I'm just going to write dr here to indicate double root. Here, to solve for x, I would first subtract 25, and then take the square root. Because it's a negative, I have the I, and the square root of 25 is 5, so plus or minus 5i. So when I look here, I am listing my zeros, there are 4 of them. X equals 0, which is a double root, so we count it twice, 1, 2, and then the plus is 1, 3, the minus is another, 4. So I have verified that the fundamental theorem is working because this is degree 4, and I have 4 zeros including my double root. All right, so the other one that I wanted you to do was number 4. So that one was k of x equals x cubed minus 7x squared plus 4x minus 28. So set it equal to 0 first. And because this has 4 terms and there is no GCF, that means I really have no other choice but to factor it by grouping. So group the first 2, group the second 2. The GCF of the first group is x squared, which leaves me with x minus 7. GCF of the second group is 4. Remember that my parentheses have to match, and they do here. So, final factorization, I take the parenthesis that they shared and multiply it times the GCFs that were in front, which is x squared plus 4. X squared plus 4 does not factor further. It's just like what we had here. There's no such thing as a sum of squares. So I set each factor equal to 0. So x equals 7. And then here, x squared equals negative 4, which means x equals plus or minus 2i. So 1, 2, 3 zeros, and I look at my degree, degree 3, so it matches. All right, so this is half of what you're going to be doing in the homework is just, building upon the factoring that we did yesterday. The other half of the homework is going to be kind of backward of that. And we've already done this concept before. We just haven't done it including imaginary numbers. So this is where it tells you, the directions will say, find a polynomial function with indicated degree and zeros. So we are going to look at try these B, part B. So try these B, part B at the bottom of the page, where it says that n is 4 and the zeros are plus and minus 1, plus and minus 5. So we need to write the polynomial function that has degree 4 with these zeros. So we have done this before. If we know the solutions are the same as zeros. So having these zeros means that I know x equals 1, x equals negative 1, x equals 5, and x equals negative 5 are all solutions. If I know the solutions, that means I know the factors, because if I get these equal to 0, x minus 1 equals 0, x plus 1 equals 0, x minus 5 equals 0, x plus 5 equals 0, I now have 4 linear factors. And so, to find the polynomial, I just need to multiply all of these 4 factors together. Now, that can be tedious sometimes. So this is going to be my f of x. In this case, it's not too bad because both of these are a sum and difference pattern. So I know that my inners and outers are going to drop out when I multiply these two together, and I'm going to get x squared minus 1. Instead of taking that and multiplying it times x minus 5, I would multiply these two together next, because that gives me x squared minus 25. And so now I have 2 factors. Even though they're quadratic, I can still FOIL since they're both binomials. So first, x to the 4th, outside minus 25x squared, inside minus x squared, and lasts plus 25, which gives me my final answer, f of x equals x to the 4th minus 26x squared plus 25. So I have now a polynomial function. It has degree 4, and if I were to work backward through my steps, I would find that its 4 zeros are positive and negative 1, positive and negative 5. So very similar to what we did in Unit 2 with the quadratics. Now, if we look at the next page, these ones are a little different because we have complex roots. Now, I would encourage you here to look at their examples, because I'm not going to do all of them. This gives you some more examples. So here, zeros 3 and 4i, and then they're telling you, how to work through the rest. And here's another one, 1, -1, 1 plus 2i. So please go ahead and look at those examples as well if you need more than what I'm going to do here. So I'm just going to look at try these C part B. So back to the one I can write on. So try these C and part B, which n equals 4 is what they gave us. And then they say the real or complex roots are x equals 3, x equals -3, and x equals 1 plus 2i. So here they gave me the x equals step, so that's nice. It makes it a little easier to start. So this factor would be x minus 3 equals 0. This one would be x plus 3 equals 0. This one over here would be x minus 1 minus 2i equals 0. Now, before we get all crazy and start multiplying, you need to put like a big star in the margin here or somewhere where you're going to see it and write complex zeros always come in pairs. And we call those pairs conjugates. So they only listed for us one complex zero. That's because they want to make sure that you know that even if they don't tell you, that means that x equals 1 minus 2i has to be a 0 also. That's not just us guessing, that's true because this 1 plus 2i and 1 minus 2i are complex conjugates. And so they have to be both there together. So that means that I have a fourth factor, x minus 1 plus 2i equals 0. So I've got x minus 3, I've got x plus 3, I've got x minus 1 minus 2i, and I've got x minus 1 plus 2i. So f of x is going to equal the product of those. Now, another hint, you should always multiply the complex ones times each other first. And additionally, if you can handle it, if you notice this, if you group these and make the x minus 1 your first term and the minus 2i or plus 2i your second term, you can actually FOIL this. So first would be x minus 1 squared. My outsides and my insides are going to drop out because they're opposites, and then I would end up for my last with minus 4i squared. So x minus 1 squared is x squared minus 2x plus 1. I squared is -1, so that turns this into a plus 4, and I get x squared minus 2x plus 5. Now, if what I did with this grouping just totally blew your mind, know that you don't have to do it that way. You can make yourself a 3x3 box and multiply it out that way. But I just wanted to show you a shortcut because I know some of you, are ready for that. If you're not, no shame, it's okay. You can make this box, and when you do, minus x minus 2ix minus x plus 1, positive 2i, here's 2ix minus 2i, and then negative 4i squared. Notice that these guys cancel each other out. These guys cancel each other out. Negative 4i squared is the same as positive 4. So these are like terms that give me the 5. These are like terms that give me the negative 2x. So you will get the same answer if you box it out. This guy is a difference of squares. So I know that that is going to give me x squared minus 9. So f of x now equals this. Now I can't FOIL this one, so not quite as easy as what I had on the previous example, because I am going to have to either double distribute or box multiply, whichever way you prefer to do it. On this one I prefer the box rather than double distribute, but if you prefer double distribute, have at it. So x squared times x squared is x to the fourth. Oops, sorry, that looks like a 9. Then this one gives me negative 2x cubed. And here I get 5x squared. Down bottom row, minus 9x squared, a positive 18x, and a minus 45. So my final answer, f of x equals highest exponent is x to the fourth. Then I've got minus 2x cubed. It's my only cubic term here. Then my x squared terms, I've got minus 4x squared. Then I only have one linear term and one constant, so I just bring them down, and then this right here is my final answer. All right, so if you need to rewatch the video, it is linked on the website, or if for some reason, there were technical difficulties and you need to finish it, but it's linked on the website. So feel free to come back to it if you need to, and homework is listed on your syllabus.